Ever really stopped and thought about, like, what a number actually is? You know, like, beyond just using it to count things.
Yeah.
Or, like, if that perfect circle you can picture in your head, does it, like, actually exist anywhere outside of your mind?
Mhm.
You sent us some really cool stuff that shows how thinkers in the medieval Islamic world, they weren't just doing math, they were actually wrestling with these big philosophical questions about what math is.
Right.
So let's kind of dive deep into their thinking and see what they were grappling with.
Absolutely. Yeah, the material you sent over the entry from the Stanford Encyclopedia of Philosophy on Arabic and Islamic philosophy of mathematics, it's a really fantastic resource for understanding how these thinkers saw math.
Yeah.
It's important to get that for them, math wasn't just this like tool for crunching numbers or solving equations.
Right.
It was really deeply tied to their broader philosophical questions about, the nature of reality, how we know things. So in this deep dive, we're going to try to unpack some of the core debates they were having. And what's so fascinating is that their ideas, they still resonate today.
Yeah, they really do.
So we're going to explore their ideas about what mathematical objects are or even what they aren't.
Okay.
Their struggle with the concept of infinity,
Yeah.
their understanding of continuity, and even their theories on how we even gain mathematical knowledge in the first place.
And I think it's important to note here for our listeners, like, why should we care about these debates about math from centuries ago?
Right.
I think it can feel very cut and dry, but I think if you are working with complex data right now,
Yeah.
or if you're trying to understand a system that has a lot of different parts,
Mm.
or even if you're just curious about how we think abstractly,
Mm.
I think this deep dive is going to give you a really interesting new perspective.
Absolutely.
We're going back in time to see how these thinkers acted as philosophers and tackled these like foundational questions about a field that can seem purely technical. And you might be surprised by how relevant their ideas still are today.
Absolutely.
Okay, so let's start unpacking this with a really basic question. Like, what did these philosophical minds think mathematical objects actually were?
Right. So this was a big one, a central question that they debated from different philosophical angles.
Okay.
And early Muslim intellectuals, they were definitely aware of and influenced by the ideas of like Pythagoras and Plato.
Right, those big names.
Exactly, those big names. And you see traces of the concept of separated mathematical objects. This idea that math exists kind of independently of the physical world
Okay.
as these like immaterial substances.
Yeah.
And also this idea that mathematical objects are actually the fundamental principles that make up nature itself.
Interesting.
And these influences, they came through translations of thinkers like Nicomachus Proclus Iamblichus,
Okay.
and they shaped the views of early figures like the Brethren of Purity and some of the early Mutazilites.
So at first you had these kind of like big picture ideas, like math existing in this separate perfect realm, or math being the actual building blocks of like the world we see.
Exactly.
But then you have Avicenna who comes along, and it seems like he really challenged those ideas.
Yeah, he really did. He was a true critic.
Yeah.
He presented this very important and influential critique against both the separateness of mathematical objects, which we can call SM for short,
Okay, SM.
and the principalness of mathematical objects, which we can call PM.
Okay, so SM and PM.
Exactly. And he really challenged these arguments for separated mathematical entities.
Okay.
He pointed out very astutely that just because you can define a mathematical object without referring to matter, it doesn't logically mean that it exists independently.
So just because I can talk about the number 5 without needing to have 5 apples in front of me,
Right.
doesn't mean that the concept of 5 is just floating around out there in space.
Exactly. And he emphasized this key difference between defining something without the condition of materiality
Okay.
versus defining it with the condition of immateriality.
Okay, so like one is saying it doesn't need matter, the other one is saying it is immaterial.
Exactly. And he argued that mathematical objects, they fall into that first category. They don't need to be immaterial for us to define them.
Interesting.
And his rigor didn't stop there. He also addressed this idea of PM, that mathematical objects are like the fundamental principles of nature.
Okay.
And he said even if they were separate, even if SM was true, it wouldn't automatically mean that they're the only separate things,
Right.
or that they have to be the foundational principles of the world.
Could be something else entirely.
Exactly. There could be other non-mathematical separate entities out there.
Okay.
And he also raised this really interesting epistemological problem.
Okay.
He said, if sensible objects the physical things we can sense and separate mathematical objects?
Okay.
If they're supposed to have similar essences, how do we ever come to know these separate immaterial mathematical objects?
It's a good question.
Right, because we're kind of stuck in our sensory experience of the material world.
Right. And as the entry points out, this line of thinking really foreshadows some later criticisms of Platonism, Okay. like Benissarov's critique.
Interesting. So it's really building on these ideas.
Yeah, absolutely.
So Avicenna is really kind of dismantling these earlier Platonic and Pythagorean views.
He's really doing some philosophical analysis here.
He is. So what did he offer as an alternative, and what were other thinkers saying around the same time?
Right. So Al-Farabi offered a really fascinating kind of intermediate position.
Okay.
And he was following the Aristotelian tradition of classifying the sciences.
Okay.
So he argued that mathematical objects are abstracted from matter in our faculty of estimation, or WAM. Yeah, it's like a cognitive power of apprehension.
Okay.
But they don't actually exist separately from matter out in the world.
So it's like our minds have this ability to sort of like pull out the mathematical properties from physical things.
Exactly.
Like seeing the shape of a ball without the actual ball itself.
Yeah, like extracting the shape from the ball.
Right. But that shape doesn't then go off and exist on its own.
Okay.
So for Al-Farabi, mathematics occupies this unique space philosophically.
Right.
It sits between metaphysics, which deals with things completely separate from matter,
Okay.
and physics, which deals with things that are inherently material.
Okay. Got it.
So the connection to matter in math, it's stronger than in metaphysics, but weaker than in physics.
So it's like this in-between state.
Exactly, an in-between state.
Okay.
And he also made this really important distinction between applied or practical mathematics,
Okay.
which deals with numbers and shapes as they're like instantiated in real things.
So like actually counting objects or measuring land.
Exactly, counting objects, measuring land, things like that.
Okay.
And then pure or theoretical mathematics, like arithmetic and geometry,
Right.
which considers these abstract concepts of number and shape without needing specific physical examples.
Okay, so one is more like practical in the world, the other one is more theoretical.
Precisely.
Got it. And Avicenna, he builds on this idea of abstraction, right?
He does.
How did he see it differently?
So Avicenna, he elaborated that mathematical objects exist extramentally,
Extramentally meaning,
meaning outside of our minds,
okay, outside of our minds.
but they're always linked to some kind of matter, like wood or gold.
Okay.
And our faculty of estimation, this WAM,
Right.
allows us to abstract them in our minds,
Okay.
to separate the concept from that specific material thing.
Got it.
But even in our minds, he thought they still had this material basis.
Okay.
He viewed numbers and magnitudes as accidents or properties of physical objects.
Mm.
And while magnitudes like shapes are always tied to materiality even in our minds,
Okay.
he thought that numbers could be considered separate metaphysically.
Okay.
However, for mathematical study to even make sense, numbers have to be able to increase and decrease,
Right.
which links them back to the properties of things that can be counted and measured.
Okay, so this is where it gets really interesting, right?
Yeah.
So was Avicenna saying that perfect circles and perfect numbers actually exist in the world?
Right. That's a big debate, big interpretive debate.
Yeah.
There are two main interpretations. One sees Avicenna as arguing that mathematical objects are primarily mental constructions.
Okay.
So abstraction is the active process of building these perfect mental pictures based on our senses.
Okay.
The other view is more literalist. It suggests that these objects actually exist in the physical world as properties of matter.
Okay.
And abstraction is how we grasp those pre-existing concepts.
Okay, so one is mind, one is world.
Exactly.
And the problem with the worldview, I guess, is that we don't really see perfect things.
Exactly. The major challenge for the literalist view is that physical objects are imperfect.
Right.
No physical circle is ever perfectly circular.
Right. It's always going to have some flaw.
Exactly. And to address this, some argue that Avicenna actually did believe in perfect mathematical objects, even though our perception of them is flawed.
Interesting.
Yeah, so there's still debate about that.
So this idea of WAM being how we understand math, that seems to have really influenced later thinkers.
It did absolutely. In post-Avicennian thought, math became more and more understood as an estimative science,
Okay.
deeply connected to this faculty of WAM.
But there were other views out there, too.
Yeah, it's important to remember that pre-Avicenna, there were other perspectives.
Yeah?
Like al-Biruni and Ibn al-Haytham. They lean toward the idea that mathematical objects exist in the world and are abstracted through imagination, or
Oh,
takayul.
do?
Yeah, and Ibn al-Haytham even proposed that these imagined forms, they have an even more real existence in our imagination,
Oh.
which is a fascinating idea. And he highlighted this idea of tamiz, or distinction, being crucial in this process.
So you've got this whole range of positions, from math being rooted in the physical world to being a product of our mind.
Right, a whole spectrum.
And it sounds like the pendulum swung more toward the mental side after Avicenna.
It did, yeah. Criticisms of his views about math objects existing in the world led to what we might call a mental turn in philosophy of mathematics.
Okay, a mental turn.
Yeah, and for example, Surawardi, he argued against the idea that numbers are just accidents of things.
Okay,
He used the example of fourness,
okay.
and he said fourness, it can't fully exist in each of four individual things.
Right.
Nor can it be just a part of fourness.
So where does it exist then?
Right, exactly. So he concluded that numbers and math objects more broadly are only mind-dependent, or itibari.
Natibari.
Yeah. And Muladra, he agreed with this view, saying that while pluralities exist in the world, it's our minds that make them into a unity that we can count.
It's like our minds are imposing the math onto the world.
Yeah, exactly.
So how do they reconcile this with the idea that math is objective and universal?
Right, because if it's all in our minds, how can it be true for everyone?
Right.
So this is where the concept of nafs al-simar comes in.
Okay, what's that?
It's often translated as the thing itself.
Okay.
It's a complex idea, but it refers to a kind of mind-independent reality.
Okay, so like how things really are.
Yeah, exactly. And some philosophers like Al-Lushi and later Al-Jurjani, they use this idea to argue that even if mathematical objects are mental,
Right.
our judgments about them can still be true independently of our minds.
That's interesting.
Right, so Al-Jurjani said that our estimations in math are different from, like, fictional imaginings.
Okay.
They're formed correctly according to this underlying reality of nafs al-wura.
Okay.
So we can still have objective math truths, even if the objects themselves don't exist in some separate realm.
Okay, so it's like our minds are tuned to this true reality.
Exactly.
So what about algebraic objects? Like they seem different from numbers or shapes.
That's a really good point. They do seem different.
Yeah.
And algebraic unknowns, what we call variables now,
Right.
they can represent either numbers or magnitudes.
Okay.
So their ontological status is kind of a hybrid.
Okay.
And interestingly, there wasn't as much philosophical discussion about them compared to numbers and magnitudes.
Really?
Yeah, but some scholars suggest that the development of algebra itself by Al-Khwarizmi might have pushed thinkers like Al-Farabi and Avicenna to think about a broader category of abstract things, or ashi,
Basha.
yeah, that could include these new algebraic objects.
Interesting.
So they were really pushing the boundaries of their philosophical category.
Yeah, they were really thinking about this stuff.
They were.
Okay, so that gives us a good idea of how they saw math objects.
It does.
Now let's talk about infinity. It sounds like they had some strong opinions about whether anything could actually be infinite.
They did. There was this widespread idea of finitism.
Finitism.
Meaning the belief that nothing in reality can actually be infinite.
Okay.
And thinkers like Thabit ibn Qurra, they even engaged with this idea of different sizes of infinity,
Why?
which is a pretty advanced concept.
Yeah.
And Yahya ibn Adi, he offered various arguments against infinite numbers,
Okay.
but there were three key arguments for finitism that became really prominent and influential.
Okay, let's hear them.
So the first one is called the collimation argument, or Burhan al-Musamita.
Burhan al-Musamita.
Yeah, so imagine you have a line segment
Okay.
that's rotating around a fixed point and it extends infinitely.
Yep.
And then you have another infinite line that's parallel to the first line's starting position.
Okay, got it.
The argument says that as the first line rotates, it has to intersect with the second line at some point.
Right.
But the idea of a first moment of intersection leads to a contradiction.
How so?
Well, for any moment you say is the first, you can always imagine an earlier moment where they were already intersecting.
Right, you can always go smaller.
Exactly. And this contradiction, the argument says, shows that the idea of actually infinite lines can't be true.
Okay, so it uses motion to sort of disprove infinity.
Exactly. And this argument was used in a lot of ways.
Like how?
Well, Al-Key used it to argue against traveling an infinite distance in a finite time.
Okay, that makes sense.
And Avicenna used it against an infinite void and actually infinite magnitudes.
So it had a lot of applications.
It did, but of course not everyone agreed with it.
Right, there are always counter-arguments.
Of course. So thinkers like Abu al-Barqari and Al-Lay, they criticized it.
Okay.
While others like Fakhr al-Din al-Razi and Mullah Adra, they defended it.
So there was a lot of debate around
Oh,
this.
yeah, lots of debate.
So what was the second argument against infinity?
The second one is called the ladder argument, or Burhan al-Salam.
Burhan al-Salam.
Yes, so imagine two infinite lines starting from the same point and making an acute angle.
Okay, like a narrow V shape.
Exactly, and then imagine an infinite series of parallel lines cutting across those two lines.
Okay, I'm picturing it.
As you go further down the angle, each parallel line is longer than the one before it.
Right, because the angle is widening.
Exactly. And now think about the line that connects the endpoints of all those parallel lines.
Okay, the line that forms the outer edge of the ladder.
Yes, exactly that line.
Okay,
That line has to be longer than all the infinite parallel lines, so it must be infinite too.
okay.
But it's also clearly bounded by the two original lines that make the angles.
Right, so it's finite too.
Yeah, exactly. So it's both infinite and finite, which is a contradiction.
Right, you can't have both.
Exactly. So this leads to rejecting the possibility of actually infinite lines.
Okay, so it's kind of like a trick of geometry.
Yeah, you could say that. And this argument has roots in Aristotle's work and was further explored by Avicenna.
So again, building on those ideas.
Absolutely. And again, there were criticisms from people like Abu al-Barakat and al-Qazwini,
Okay.
and defenses from Alusi and Muliadra.
There's always this back and forth.
Yeah, always a lively debate.
Okay, so what's the third argument?
The third one is called the mapping argument, or sometimes Burhan al-Taybuk or al-Taybik.
Those are some long names.
They are, yeah. So for this one, imagine an infinitely long line.
Okay, an infinite line.
Now, remove a finite segment from that line.
Okay,
The remaining part is still infinite, right?
it has to be, yeah.
Now, try to match up the points on the original line with the points on the remaining line.
Like a one-to-one mapping.
Exactly, and they would match perfectly, right?
Right, because they're both infinite.
Oh! But according to Euclid, things that correspond exactly are equal in magnitude.
Okay.
And the whole is always bigger than any of its parts.
Right,
But here we have an infinite line that seems equal to a part of itself.
which is a contradiction.
Exactly. So the initial idea of an actually infinite line must be wrong.
Okay, so it uses the idea of parts and wholes to kind of break infinity.
Yeah, that's a good
Yeah.
way to put it. And earlier versions of this argument were present in Al-Kindi's work.
Okay,
And Avicenna gave us more precise versions.
building on it again. Always building, right?
So this argument, it wasn't just used for lines, right?
No, they also used it for collections of things like numbers.
Okay.
So they realized that you could match up an infinite set of things with a smaller infinite subset, like matching all the natural numbers with just the even numbers.
Okay. Yeah, I see how that works.
And they found this to be just as paradoxical.
Right, because how can a part be equal to the whole?
Exactly. Avicenna seemed to understand this implicitly.
And Fahar al-Din al-Razi, he explicitly used these kinds of examples.
So they were extending the argument.
Yes, they were. And even al-Ghazali mentioned this argument, and it actually made its way into Western thought pretty early on.
Wow.
Yeah. So it's interesting how these ideas traveled.
It really is. So these arguments against infinity, they started with the physical world, but then they had implications for math objects too.
Exactly, especially for those who thought math objects were like literally part of the physical world.
Right.
So if infinite things can't exist physically, then they can't exist mathematically either.
Okay.
But those who rejected that view, like Fakhr al-Din al-Razi,
Right.
they could have different ideas about mind-dependent infinities.
Because those wouldn't be limited by the physical world.
Exactly, and it's interesting that Ibn al-Haytham even argued that we can't actually picture an infinite line in our minds.
So even our imagination has limits.
Apparently so.
Okay, so their ideas about reality really shaped their ideas about infinity.
They were thinking about it all as connected.
Okay, so let's move on to another big concept, continuity.
Okay.
How did they approach the question of whether things are fundamentally continuous or made up of little indivisible parts?
So this question was closely tied to the debate between atomism,
Atomism.
the idea that everything is made of these tiny indivisible atoms,
Okay.
and holomorphism,
Holomorphism.
which is the Aristotelian view that things are made of matter and form,
Okay.
allowing for continuity.
Okay, so one is wholeness.
Yeah, that's a good way to put it. And Avicenna, he saw a strong connection between mathematical and physical continuity.
Oh.
He believed that just like geometric shapes are continuous without actual separable parts,
Okay.
so too are the dimensions of physical objects.
So like the length of the table is continuous.
Exactly. And he used this idea to argue against atomism.
If things are truly continuous, you can't have atoms.
Precisely. But other thinkers tried to find ways to reconcile continuity in math with atomism in the physical world.
Okay, how do they do that?
Well, Shahrastani, he was skeptical of whether our ability to imagine infinite division in math
Right.
actually tells us anything about the physical world.
Right.
He said that maybe physical things are actually made of a finite number of parts, even if we can imagine dividing them forever in our minds.
So our math might be continuous, but reality might not be.
Exactly, and this allowed both views to exist.
Interesting.
Yeah, Al-Razi had a slightly different approach.
Okay.
He thought that what we can imagine determines what can be divided in the world,
Okay.
but he thought there's a limit to how small we can imagine.
So at some point it becomes impossible to picture.
Exactly. And while he accepted infinite divisibility in geometry,
Okay.
he didn't think it represented the real world, which he thought was atomistic.
Okay.
And later atomist philosophers like Al-Lishi, they often said that continuity only exists in our estimation, not in reality itself.
So again, this idea that math might be describing things differently from how they really are.
Yeah, exactly.
So their beliefs about reality really shaped how they understood continuity.
Absolutely. It was all connected.
Okay, so let's shift gears and talk about how they thought we learn math.
Okay.
Like, what were their ideas about how we come to know mathematical concepts and truths?
So they generally agreed that sense experience was the starting point for learning math.
Okay.
But how we go from senses to abstract ideas was debated.
It makes sense. You had to experience the world to learn.
Right. And Avicenna, he famously argued that sense perception is essential for even forming math concepts.
So we can't just think our way to math. We have to experience it.
Exactly. And he even used the thought experiment to make this point.
Oh, interesting. What was the experiment?
The entry doesn't give us the details, unfortunately.
Okay.
But the main point is that he thought without senses, we couldn't grasp mathematical ideas.
Okay.
Now, depending on how you interpret Avicenna's overall view,
Okay.
the next steps in learning math differ.
So what are the different interpretations?
One view is that our faculty of estimation, or WARM,
Right.
helps us perceive mathematical properties in physical objects.
Right.
Like seeing that two apples have two-ness,
Okay.
and this is guided by common sense.
Okay, so we're directly perceiving the math in the world.
Exactly.
Okay, what's the other view?
The other view says that estimation and imagination work together to create perfect mental objects
Okay.
that don't necessarily exist in the world.
So our minds are constructing the math.
Yes.
So it's either perception or construction.
Exactly. Two different approaches.
Okay, so what about abstract concepts like, since WAM is tied to our bodies, how do we grasp abstract math?
Right. So they brought in the idea of the active intellect.
The active intellect.
Yeah, it's a philosophical concept that explains how we grasp universals.
Okay.
But there were different views on its role.
Okay.
Some thought it emanates those universals into our minds,
Right.
while others saw it more as a reservoir of knowledge that we can access.
So like a library of concepts.
Exactly.
Okay.
Now, Ibn al-Haytham, he offered a simpler explanation.
Okay.
He emphasized imagination for creating perfect math objects and distinction for conceptualizing them.
Okay.
So he didn't really need the active intellect.
Interesting.
Yeah, al-Biruni, he was a bit unsure.
Okay.
He wavered between WAM and intellect as the main faculty for understanding math.
So he was on the fence.
Yeah, you could say that.
And Napp's Albert, that comes up again here, right?
And it does in some later theories.
Okay.
They said that senses estimation and intellect all work together to grasp math entities as they are in Naff's al-Awar.
So like we're tapping into that true reality.
Exactly. But how we do that exactly remained a mystery.
It's always good to have some mystery.
It keeps things interesting.
Okay, so what about the basic principles of math, like axioms and postulates?
Right, those foundational truths.
How did they think we know those?
So there was this general belief in foundationalism.
Foundationalism.
The idea that math knowledge is built on these basic concepts and propositions.
Like building blocks.
Exactly, and Avicenna, he categorized these propositions into two types.
Okay, what are they?
Al-Waliyat, which are primary data, and Fi'riyat, which are data with built-in syllogisms.
Okay.
So Al-Waliyat are self-evident truths.
Okay.
Like the whole is greater than the part.
Okay, that seems obvious.
Right, and Fi'riyat require a simple syllogism.
Okay.
Like 4 is even.
Okay.
Avicenna said, we assent to both types through the natural operation or fiat of our intellect.
Fidea.
Yeah, so they're a priori,
Okay.
meaning we know them independently of experience,
Okay.
but only after we grasp the concepts.
So we're not born knowing them.
Right, not necessarily. And
Yeah.
Al-Farabi and Al-Lisi, they had similar views.
Okay.
But there were also more empirical approaches.
Okay.
Like Ibn al-Haytham, he later argued that even axioms, like things that correspond or equal,
Okay.
we accept them because of repeated experience.
So we learn them through our senses.
Yeah, in a way.
Okay.
And he even gave an argument for the whole is greater than the part based on our senses.
Interesting.
Yeah, and this view influenced later thinkers too.
So it's this tension between innate knowledge and learned knowledge.
Exactly.
Okay, finally, the entry mentions ars analytica and ars inveniendi. What were those about?
So these terms refer to art of analysis and art of discovery.
Okay.
And they were interested in how mathematicians actually discover new truths.
Versus how they prove them?
Exactly. And Thabit ibn Qurra, he explored this early on.
Okay.
But his grandson, Ibrahim ibn Sinan, really developed this area
Okay.
with his work on analysis, or talil,
Top level.
yeah, in synthesis, or tarkib in geometry.
Okay.
He looked at how to analyze problems to find solutions,
Okay.
and then how to turn those solutions into formal proofs.
So it's about the process of mathematical thinking.
Exactly. And Al-Sizi, he wrote about problem-solving methods.
Yep.
And Ibn al-Haytham, he had a major work on analysis and synthesis.
So they were really digging into the how of math.
They were, and they even talked about undecidable problems.
Undecidable problems meaning?
Problems that we might not be able to prove or disprove.
Oh, wow. So they were thinking about the limits of math.
They were, which is really impressive.
It is. So they weren't just doing math. They were thinking about how we do math.
Exactly. They were true philosophers of mathematics.
Okay, so let's talk about the last part, applicability and reliability.
Right. So given all these debates about what math objects are and how we know them,
Yeah.
it's natural to ask how well math describes the real world.
Makes sense?
If you think math is just in our minds,
Right.
it's harder to explain how it can give us true knowledge about the world.
Right, because it's not connected to anything.
Exactly. And those who held this view, they often saw math as less certain or less valuable than other fields like physics or metaphysics.
Okay.
Because those fields were seen as dealing more directly with reality.
Got it.
Some even argue that Avicenna thought math was less useful in this way.
Interesting.
Yeah, and Averroes, he believed that math being detached from reality made it less important for human understanding.
Compared to physics and metaphysics. And the atomists, they were also skeptical because math relies on continuity.
Right, they thought the world was made of discrete parts.
So continuity wouldn't apply.
Exactly, and Fakhr al-Din al-Razi, he argued that Euclidean geometry can't accurately represent an atomistic world. And Al-Jiji, he even called math objects frailer than a spider's web.
Wow.
He was questioning how reliable they can be.
Right.
And Al-Bukhari, he agreed that math is less reliable than physics and metaphysics for understanding real things.
So there's this real challenge to explain why math works so well.
Yeah, if it's just in our minds or if it's based on continuity.
Right.
But this is where Al-Jurjani and Nafs al-Nur come in again.
Okay.
He argued that even if math objects are in our imagination,
Okay.
we imagine them correctly.